The worlds of technology, health, transportation, they need materials to be less dense but without compromising on strength, so that they are better suited to their applications. There has been a huge surge in the research of lighter materials that have higher strengths because not only can they make processes more efficient, they are crucial to preventing health problems. Most human body implants are currently made of titanium, which has 3 times the density of bone, just so it can match its strength. But this takes a huge toll on the bone around the implant, degrading it tremendously. Because the implant is so dense, it causes stress shielding, where stress that's vital to the bone's regeneration and growth is taken away and exerted on the implant instead. This leads not only to a shorter lifetime for the implant, but also for the bone. After observing these needs, I ideated a method that can make any material lighter without compromising on strength. Bioimplants, mobile tech, vehicle bodies, the possibilities are endless. But in order for the possibilities to be endless, I had to think of something every metal or alloy has in common and innovatively alter that property. Since this is one of the biggest sought-after issues, scientists have covered a lot of ground in this subject. There are several alternatives to conventional metals today, such as plastic polymer-based composites like carbon fiber, but this is not a method that can be applied to every metal. It's just one method that has certain properties, and since you're stuck with these set of properties, it can't be used for several applications. On the atomic scale, making a material porous is the most common way to make any metal lighter, but this shows a huge decrease in strength, almost by a factor of 10 to the 5th. Recently, however, Dr. Srinivasan discovered that niobium, when used in small amounts, can be very strong and stiff. So I took these 2 ways to alter materials, saw the advantages and disadvantages of both methods, and combined them to eliminate all the drawbacks and just keep the positives. This is innovative not only because I combined 2 methods, but it's also manipulating a metal on the atomic scale, which is a field common to all materials. I used computational simulation with LAMMPS to test my method on a copper model system. Specifically, I created the systems using Oviedo to create the pores, and then LAMMPS to initialize niobium nanorods in these pores and reinforce them. I tested each system under compression and tension, and extracted the properties strength, stiffness, and density. I first started with spherical pores, formed the control, and then reinforced a single pore geometry with a single nanorod. Once it showed an increase in strength and stiffness, I moved on to prove my method on an irregular pore system, one that actually occurs in nature. I found that my method increased the stiffness 40% over the control, and just 2 nanorods increased the strength 70% above the control, even after the 80% loss in density. My final step was to cement my method by translating these results to a laboratory model of zinc, reinforced with zinc oxide nanorods. At the University of North Texas's Material Sciences Labs, the system was created by my mentor's fellow professors, and nanorods were able to be placed exactly where needed in the pores. By proving that this method works on a zinc oxide system, I also illustrated the versatility, since it shows the same results for both copper and zinc oxide. My 2015 Google Science Fair project submission is a novel method that can make any metal or alloy lighter without compromising on strength by making them porous and reinforcing the pores with nanorods. It is a completely new and versatile method since it can manipulate any metal's strength, stiffness, and density according to whichever application they're needed for.